Welcome to The Nadium. I'm Chris Rankin. The more I learn about this mad world, the more mysterious it seems. Time passes differently for different people. And not just that, how fast time moves changes for everyone throughout their lives. It's not just the experience of time. It's not just the feeling. I'm talking about the actual numbers of hours and seconds. This bizarre, counterintuitive, but well-tested phenomenon is part of the general and special theories of relativity. The rate time passes is never consistent from person to person or moment to moment. How fast the clock moves actually depends on altitude and geographic location, how fast one is moving, and even the relative positions of other planets in the solar system. Time dilation is not very noticeable in daily life, but it's very relevant in particle physics and satellite communications. This weird effect, revealed to us by Albert Einstein, is now accepted by the entire scientific community. The fuzziness of time must even be accounted for in the signal processing and timing of satellites and spacecraft. Time dilation refers to the strange but very real physical phenomenon that time passes at different rates for different observers depending on how fast they're moving or how close they are to massive objects. It's a direct result of Albert Einstein's general and special theories of relativity, in which time is not as absolute as it might appear. The rate it passes is different for different observers in different reference frames. Time dilation is the slowing of time as perceived by one observer compared with another due to their relative motion. It also depends on how strongly gravity is pulling on each observer. Moving clocks run slowly is a phrase used often as a concise way to describe time dilation. It gives the right general idea, but it's also somewhat misleading because it puts so much emphasis on the idea of clocks, which are not really fundamental representations of time. I think of time dilation as an unexpected side effect of the intermingled relationship of space and time, rather than just the slowing or quickening hand of a clock. Time dilation is a consequence of nature's speed limit. It's because light can only go so fast, no matter what. This fundamental and absolute limit on the speed of light means that, counter to intuition, the speed of material objects and light are not additive. In other words, it's impossible to make the speed of light appear greater by running toward the light source. Conversely, you can't make the light slow down by running away from the source. The way Albert Einstein imagined relativity was to picture a light source between two mirrors on a moving train. The light beam bounces back and forth from mirror to mirror. The time the light takes to make the journey, of course, depends on how far apart the mirrors are. However, something funny happens when the train starts to pull away and the mirrors begin to move relative to us, the outside observer. If we look carefully, we can see the light beam actually has a greater distance to travel between the mirrors when the train is moving. The light has to account for the horizontal motion of the train. Every process, physical and biological, has more ground to cover when the whole thing is moving. Motion and mass stretch space out in a way, and it makes everything happening in that reference frame slow down. The faster the relative velocity, the greater the time dilation between one observer and another, with time slowing to a stop as one approaches the speed of light, or 186,000 miles per second. This is when time dilation really shows itself. There are tiny, elementary particles called muons, created when cosmic rays collide with Earth's upper atmosphere, and they can travel at nearly the speed of light. The muons are very unstable and don't have very long lifetimes. They normally decay into simpler particles in a small fraction of a second. Even with their extreme velocities, muons shouldn't last nearly long enough to reach Earth's surface. Yet, Many of them do. Muons are detected all the time on the Earth's surface. The reason is time dilation extends their lifetimes by a factor of 5. Because of their speed and this time-stretching effect, the particles are able to survive effectively longer than their lifetimes and make it all the way to Earth's surface. In addition to speed warping time, gravity and massive objects do the same thing. This is because gravity distorts the fabric of space. Light has to travel farther through space that's been stretched out by gravity, so it effectively slows down. In that region of space, time slows down. Since gravity is slightly weaker on the top floor of a skyscraper than at ground level, the time dilation effect is also weaker on higher floors. In other words, time is passing more quickly at the penthouse than in the basement. Time goes faster the farther you are away from Earth's surface. Being closer to the core of the Earth, the center of gravity, slows time down. Even though the effect is too small to detect with human senses, the time difference between altitudes can actually be measured using high-precision clocks. A climber's time passes slightly faster at the top of a mountain compared to people below at sea level. It's been calculated that due to time dilation, the core of the Earth is actually 2.5 years younger than the outer surface. Gravitational time dilation is a big factor for space travel. While the astronauts' high relative velocity slows down their aging, the reduced gravitational influence in space speeds it up. This comes into play for spacecraft and satellites, due both to their high speeds and the widely varying gravitational fields they experience during their travel. For example, let's consider the time dilation effects on NASA's Voyager 1 probe in the 45 years following its launch in 1977. Special relativity, the part of Einstein's theory that deals with how speed affects mass, space, and time, predicted that the Voyager has aged 2.2 seconds less than we have on Earth. But general relativity, the part that deals with gravity, partially counterbalances this. We experience stronger gravity than the Voyager, so in this sense, the probe has aged about 1 second more than we have. If we combine these two effects from the general and special theories of relativity, Voyager still turns out to be younger than us Earthlings, but only by about 1.2 seconds. Calculations like this can be very important in situations in which precise timing is critical, like the case of GPS satellites used for navigation. For example, timing errors of just a few hundred nanoseconds or billionths of a second can lead to positioning errors hundreds of meters, which could be a problem if your phone is giving you directions over the Bay Bridge. To achieve a usable level of accuracy, the GPS system has to account for time dilation, which can amount up to 38 microseconds or millionths of a second per day. And this time dilation can be taken to extremes. Imagine a spaceship traveling from Earth at 95% of the speed of light to a planet 9.5 light years away. An observer on Earth would measure the journey time as distance divided by speed, or 9.5 divided by 0.95, or 10 years. The spaceship crew, however, would experience time dilation, and therefore perceive the trip as only taking about 3 years. In other words, between leaving Earth and reaching their destination, the crew members age a little over 3 years, while 10 years have passed for people back on Earth. Although really striking situations like this involve enormously high speeds, time dilation occurs with any relative motion. For example, a regular flyer who crosses the Atlantic every week would have experienced about 1,000th of a second less time than a non-traveler after about 40 years. This doesn't begin to cover the weird implications of Einstein's theories. It might even get stranger than time dilation. Moving objects also contract in physical dimension the faster they move. What all this tells me is that humans experience a highly distilled version of reality that may have led to a lot of oversimplifications and maybe silly assumptions about the way the world works. For me, figuring things out has often come down to being able to finally throw away false, encumbering assumptions. These things are like blindfolds, holding you back from seeing what's plainly obvious. I will say that getting rid of them is sometimes easier said than done. Thank you very much. This was Chris Rankin with Vanadium.